So today, the topic is, as we said, approximating areas. Let me open this up from the textbook. And first, we will just talk about the sigma notation. So I will just introduce the sigma notation to you. So the sigma, or the summation notation, is used and we have a long sum when we add multiple expressions, several numbers. So instead of writing them all one by one, we just use a shortcut. So we just use this sigma letter. So this is the Greek letter sigma, Greek capital letter. And we just use it as a shortcut to denote some numbers. So the notation goes like this. So inside, after this sigma letter, we have some numbers or we have some expressions. And this sigma notation has one index, okay? So the index changes between two numbers. So this is the lower limit. It starts from 1, and let's say it goes until 10. And this expression tells us to keep adding the expression inside. So you can have different expressions after the sigma sign. So whatever you have here, you just change its value starting from 1 until 10 and keep adding them. Okay, so what does it look like? So this tells us to plug in the value here, so which is 1, and add, so plug in the next value, which is 2, plug in the next value, so just add numbers from 1 to 10, okay? Okay, so this is the lower limit of the sum, and this is upper limit of the sum, the number we put on the top, and this number I is what we call the index. It's sometimes called the dummy variable because you can just use any other letter apart from I. You can use K or J, so those are also used. So in the formula, what you have inside the formula, you just give numbers starting from the lower limit until the upper limit, and you add. So let's see an example. Write in sigma notation and evaluate the sum of the terms 2 to the I for I changing between 3, 4, 5, and 6. Okay, so what we want to do is we would like to write in sigma notation and evaluate the sum of the terms 2 to the I, and I is changing from 3 to 5 and 6. Okay, so this is the question. So we would like to add 2 to the 3, 2 to the 4, 2 to the 5, and 2 to the 6. And the shortcut, the sigma notation for this sum is we just make this, like put this capital sigma letter, and our index is changing from 3 until 6. Okay, so, and what do we have inside? We are just adding this expression. We are just adding 2 to the something. If you just plug it in, now if you are given this expression, you can just plug it in. So start from 3, plug in 3, it is 2 to the 3. The next number is 4, so just plug in 4, 2 to the 4. So okay, we just found, we just were able to write the sum in a compact way, okay, using a short notation, a simple compact notation. So let's just talk about a few properties of the sigma notation. So the first notation tells us, so if we have a sigma operation, which is a sum operation, and inside there is no I. Okay, so there is no I, there is just a constant number. So what does it tell us? Well, this tells us, so for each variable, for the index changing from 1 to n, only add c. So for I equals 1, the expression is just c. The expression is just c. So it just tells us keep adding c's until the index changes from 1 to n. So this is simply the sum of n times c. I will just show you the expression, and let's understand what it means. So let's evaluate this sum. Okay, so let's evaluate this sum. So we just need to understand what this notation is. So what does this notation mean? So this is the sigma sign, which tells us that some things will be added. Okay, so whenever you see the sigma, you should know that you are going to be adding some things. Okay, so the sigma notation is just the shortcut for a summation. So I just put 3 pluses, but it may be more or less. Let's see. So this is the index that is denoted. So we just put it under the sigma sign, and it changes. It starts at 1, and this number on top tells us the where to stop. I will change from 1 until 5. Okay, so you will just plug in values for I. So in fact, we will have total of how many terms in the sum? So there will be total of 5 terms added. Okay, so because I is changing from 1 to 5, for each I value, we will find some expression and we will just add them. So what are these expressions? Where do we find them? It is written right next to the sigma notation. So the expression we will be plugging in numbers from 1 to 5 is 1 over I. What does it mean? 1 over 1 over 2, 1 over 3, 1 over 4, and 1 over 5. 1 plus 1 over 2 plus 1 over 3, so plus 1 over 4. So you can just plug it, get common denominators and evaluate. But this is how we write this sum, okay, openly. Let's write in sigma notation. What do we have in here? We have a sum, right? We have a sum, and we just need to find the pattern here. What are we adding? Okay, so what are we adding, and how can we write it using a variable? So here, in fact, what do we have in the denominators? So do you see the pattern in the denominator? 4, 9, 16, and 25. What are those numbers? Those numbers are the squares of some integers. Okay, so in fact, the first one you can say this is 1 over 1. So this is 1 squared, this is 2 squared, this is 3 squared, 4 squared, 5 squared. So we can just use the sigma notation, which is going to be just the shortcut to write this sum. So we can just use this capital sigma letter. So we should determine the lower limit of the sum and the upper limit. So those are going to be determined by this, like the first and the last term in our summation. And we will have some expression inside, which is going to be the expression that is being added. Okay, that keeps being added. What we are adding is expressions of this form: 1 over something squared. Okay, so here we are just adding 1 over something squared, and what is the smallest value we plug in? So the summation starts from 1 over 1. So the sigma, like the index, sorry, starts from 1. So because the larger number here we have is 25, which is 5 squared. So I goes from 1 to 5. And we are just adding 1 over 1, 1 over 2 squared, 1 over 3 squared, 1 over 4 squared, 1 over 5 squared. So this is just a convenience notation. Instead of writing them all by one, just a shortcut for adding several numbers. Okay, 2 times 1 over 1 plus 2 times 1 over 2, 2 times 1 over 3 plus 2 times 1 over 4 plus 2 times 1 over 5. So how can we write it in sigma notation? Well, this is 2 times 1 over something. So 1 over some number, right? And what is I changing from? It is changing from 1 until 5. That's right. So again, we just went until 5. But just look at the top expression. So we see 2's appearing in every, like in each term. Well, you can just factor it out. So you can say this is 2 times 1 plus 1 over 2 plus 1 over 3 plus 1 over 4 plus 1 over 5. If there is a number multiplied by each term, we can factor that out. So in fact, we can say that this is the sum, like this is twice the sum of the terms from I equals 1 to 5 of 1 over I. Well, in fact, what we showed is that if there is some number inside the summation, so if each term has this constant common number, then you can take it outside, right? You can just take it outside. So these are equal. So this is a property that is given here in the second rule. Okay, so we just talked about this rule. If there is a difference or sum inside this sigma, I changing from some number to another number, then you can just split this into 2 parts. If they are added, you add them. If they are subtracted, you subtract them. So just keep the index, keep the upper and lower limit the same. So the sum of n integers. So this is telling us if you have integers from 1 to n added, okay? How can we write it in sigma notation? Well, here the smallest number is 1 and the largest number is n. So the limits are changing from 1 to n. But we would also need the index. Okay, so here this is just a constant number we denote. So it's changing from I is changing from 1 to n. And what is inside? We are just adding the numbers. I is 1, I is 2, I is 3. So the expressions that are being added are simply the number I. Okay, so 1, 2, 3, 4, 5. And it is given by n times 1 plus 1 over 2. If you need to add the terms like the integers from 1 to n, then you can just make use of this formula. And in fact, the derivation of this is very nice. So if you realize that if you add 1 and 100, you will find 101. If you add the second from the first and the second from the last number, this is 99 plus 2, which is also 101. And if you add the number third from the first, and third from the last, 98 plus 3, this is also 101. How many of them there are here? So if you keep going from 1 to just 50, and then if you just go in the reverse order, 51, 52, 53 until 99 and 100, the sum of each will be 101. So the number we go up to is 100 in this case, times 101 divided by 2. Okay, so in fact, if you just add them, there are 50 of these numbers. So there are 50 of these sums, let's say. So this is in fact 101 times 50. So the shortcut would be just multiply 101, which is n plus 1, times like half of the higher number. If you end up getting, let's say, if you need to find the sum of the first n terms, the numbers added from 1 to n, then there is a formula for that. Okay, and if you also need to find the sum of the first, the sums of the squares of the first n terms, there is also another formula which we won't go into detail. And there's also one other formula if you want to add the cubes of first n integers, then you can just use this formula to find that. So we would like to find the sum of the values of 4 plus 3i for I changing from 1 to 100. So let's write this using the sigma notation. Our index changing from 1 until 100. And what is the expression that we keep adding? Here we are given the expression, so we would like to add this expression for each I value. So what we are going to be putting on the right will be 4 plus 3i. That means just plug in, so for I equals 1, we will plug in 4 plus 3 times 1. For I equals 2, just plug in 4 plus 3 times 2, okay, and keep adding them. We can make use of the formulas we discussed. So remember, if there is some, there are two things added, we can just split the summation into two parts. So we can say this is the sum of only 4s plus sum of 3 times I. Now, we talked about this previously, earlier today. What does it tell us? So here, from I is changing from 1 to 100, but the expression inside is just a constant number. So in fact, what we are doing here is just keep adding 4s. How many times? So how many 4s are there in here? From 1 to 100. So 100 of these 4s, right? In fact, this sum, therefore, would be 4 times 100. Let's look at the second part. So we discussed that if there is some constant number multiplied by each term, we can take it outside, right? Just factor it out. So this is simply 3 times sum of the numbers I changing from 1 to 100. And so we know that there is a formula for adding numbers from 1 to 100, okay, just all the consecutive numbers. And we just talked about that formula. So what was that? It was n times n plus 1 divided by 2. Okay, so that formula we already know. So let's plug it in. So plus 3 times this formula, which is 100 times 101 over 2. Well, this is going to be 400 plus, so this is going to be 50. 101 times 50 times 3, which is 15,150. And add 400 to this, so we will find 15,550. So this is the sigma notation. If there are two things added or subtracted, we can just split that into two parts using, again, two sigmas. And if there's some constant inside, adding it 100 times is just multiplying it with that number. So there are 100 terms added in here, which are always like only some constant number. So it is 4 times 100, which is 400. And the last thing we did is, if there is a constant multiplied by the index here or any other variable, we can take it out. So it is like factoring out. I just showed you an example previously today. And you can still have this the index and the sum. And once you find it, you will just multiply by that 3. Instead of multiplying each term, you just multiply after you find the sum. And so for this sum, we just use the sum formula, which is the sum of numbers from 1 to n. So we just discussed that formula. So just plug it in and multiply it by 3 to find this sum. Okay, our main purpose for discussing this was finding areas under the curves. So if we have some geometric shapes, like regular geometric shapes, like rectangle with sides A and B, what is the area? We can multiply the two sides, A times B, to find the area of a rectangle. So if you have a square with sides A and A, what is the area? Again, just multiply the two dimensions, two sides, which is A squared. Well, we know how to find, there are some formulas on how to find the areas of triangle or like trapezoid. However, if we have a graph like this, so we may need to find the area under this graph. This shape even doesn't even have a name. Okay, so it is a shape like this. So how can we find the area under this curve? So let's say this is the graph of y equals f of x. So the idea is just make use of the shapes that you are familiar with, that you know how to find the area. Just use them to approximate the area under this weird or irregular shape. Okay, so well, you can just say, well, this is, I will take this, I will think about this as a rectangle. So I will just make use of, so I will just take its height to be this point. So I will just multiply this side, which is going to be the x coordinates of this point, right, until it goes here. So let's say this is the x coordinates, and let's make use of the height. Well, they are on these two values, heights are almost the same. So let's say this is the height of the rectangle. Well, if this is the x value, this is f of x, right? This is the y coordinates here is given by the f of x value. So you can just say that the area under this curve is approximately x times, so this height is f of x, or the y coordinate. So this is x times y. In terms of x, it is just x times f of x. Okay. So what we did here, we just used one rectangle to approximate the area under the curve y equals f of x. Okay, so until some specific x0 value, let's say this is some specific x0 value. What is different? So when we say x, it is just the variable changing, but when you say x0, x sub 0, you just specify a value like 2, like 5. Okay? Okay, here when we do this approximation, we just we just also evaluated this area, right? Well, it is not part of our shape, our 2D shape. So we just, in fact, overestimated. So we overestimated. So this rectangle overestimated the area we are looking for. So we are looking for only the yellow area. And if we use a rectangle, the rectangle is larger, so it's going to overestimate. Okay, so what can we do? How can we improve it? Let's consider a similar, like the same curve, more or less. Any ideas? How can we improve our approximation? Well, so far we used one rectangle to approximate this area. How about using more than one rectangle? Like if you just divide this area, this 2D shape, into smaller intervals, and if you just draw rectangles, so let's just use this point as the height of the rectangle. Okay, so I will just keep using the right end point of each interval. So okay, so this is the first interval. This is the second interval, right? Sub-interval. So we just divide it into sub-intervals. The right end point of each interval, so this point, I will just take it to determine the height of the rectangle that we will be using. Okay, so we can split this into sub-intervals, so they will all have the same width, but the height will change depending on this value. So we just standardized. We said that, okay, let's always stick to the right end point. Always just use the right end point of each sub-interval and create a rectangle with a fixed height. Okay, so the height normally is changing, but we are just fixing it to be like at one value. We can create, and let's do one last. Let's do it with orange. So this will be the last rectangle. Now we have several rectangles, and we can just consider finding the area of each sub-rectangle. So these are sub-intervals. We just approximate the total area as the sum of each approximating rectangle. Okay, so the yellow area will be area 1, area 2, area 3, 4, 5, 6, 7. So it's going to be the sum of these areas. How do we write it in sigma notation? Sum of the areas. So here we just used like the notation, first area, second area, seventh area. We just used A1, A2, A3. So that's why I just say AI. And I is changing from 1 to 7. Okay, so this is where we will make use of the sigma notation. Okay, the more rectangles we use, the better the approximation we find. Okay, we will find a better approximation of the yellow area if we use more rectangles. Okay, so these parts are not part of our region, but our rectangles, just evaluated them as part of the total area. However, if you consider this part in this rectangle, the yellow, this is this is part of the area, but the rectangle had a smaller height, so it didn't evaluate, take into account this purple region. Similarly here, so these parts are, let me just show them, and in fact this one too, just a little piece. So we can say that these rectangles just underestimated but A1, A2, A6, and A7, they just overestimated the area of the rectangle, I mean of the region, of the region that we are looking at. So in fact, what happens is that, so some of them underestimate, some of them overestimate. So eventually, they just you get a better approximation because they cancel each other out. In general, we will have a region. Okay, so this is the graph of the function y equals f of x, and we will just talk about like between two x values a and b. We just divide the interval a to b into smaller subintervals, and these are called partitions. Okay, so these are called the partitions. Okay, so we just divide that interval into smaller subintervals or partitions. So you can just give them, give them the names x0, x1, x2. So the first region, I mean this first subinterval, let's just call these points x0, x1, x2. So those are just to mark where we divide our intervals, where we make our partitions. So the last point, we will just name it x sub n. So the first point is x sub 0. So it's going to go until x sub n. And these are called like regular partitions. And that means we just divided them evenly. Okay? We just divided them evenly. So let's say this is a graph is changing from A to B, and we can divide it into several subintervals. In this case, this is going to be the initial point x0, x1, x2, x3, x4, and this is x5. Well, in fact, we divided 1, 2, 3, 4, 5 into 5 subintervals. So we made just 5 partitions, and we can just find the area in each rectangle. So we can, okay, so we said that in the previous example, we used the right endpoint to determine the height of the rectangle. Okay, so that means, how do we find this height? Because this is the graph of y equals f of x, the height of, the height of this point is given by plugging in x1 to this function. So in fact, let's say this is the area 1. The area of the first rectangle can be found by multiplying this distance between x1 and x0 times the height of the rectangle, which is f of x1. Okay, so we said that we will use regular partitions. So in fact, that means that these x1, x2, x3 points, they are of same, the distance between those points are the same. So we can just call that distance as delta x, okay? So we will call it as delta x. So we just divide it into 5 subintervals, each with each has width delta x. And so area 1 will be equal to the width, which is delta x, times the height, which is found by plugging in the right end points. Okay, so let me just say here we are just using the right end point. So here the right end point is x1. So we just plug it into the function to find the height of the function. We evaluate the height of the function by plugging in this point, and this will be the area for the first rectangle. Well, if you want to write this for the second subrectangle, what is the area for the second rectangle? Well, the width is the same, delta x. Let me just write it openly. So in the second area, the x distance, it changes from x1 to x2. So the width is x2 minus x1, which is delta x, times the height here is given by evaluating this function at the right end point, which is f of x2. Okay, so the same idea, we can just keep writing the other areas, A3, A4, and A5. So you can say the total area is approximately the sum of these areas where the index is changing from 1 to 5, in this case, right? A1, A2, A3, A4, A5. And what was the formula for AI? Let's plug it in. So each subrectangle, their area can be found by multiplying the width, which is constant, delta x, times the height. Well, the height, they always depend on the, in this case, we just chose it to be the right end point. So we can say the height will be found by plugging in the right end points into the function formula. Okay, so in fact, we just obtained a formula to find the total area for 5 subintervals, 5 partitions, where we used the right endpoints fx, like x1, x2, to find the height of the rectangle. What if we used the left endpoints? Let me put it on the other side. So if you just choose this point to determine the height of this rectangle, right? Then what you should do, you would say A1, the area of the first rectangle. Now you have a rectangle which is smaller, like this. So A1 would be given by this, it's going to have the same width, delta x. Now the height will be given by plugging in x0 into the function, okay, instead of x1. And you would just do the same for the second area. So the second area now will have this point as the height. So it's going to be the width, which is constant delta x, times f of x1, which gives us the height of the second rectangle. So we can just write the area. We can just adjust the formula we had here. Sum of the rectangles from like the 5 rectangles we have in here. But in this case, we just used a different height, right? Because we picked a different point to determine the height of the function. That's going to be delta x times f of x I minus 1. Okay, so here for the first rectangle, we used x0. For the second rectangle, we used x1. So for the ith rectangle, we just use the x coordinate right before, right? The index right before I. I is again changing from 1 to 5. So this will be the approximation for the area using 5 partitions again, but using left endpoints. Okay, so instead we just divided again, but we didn't use the right endpoints to determine the height, but we used the left endpoints to determine the height of these rectangles. Okay, so both are possible. So we said that as we increase the number of partitions, we will get a better approximation. And we talked about the limit idea previously in the beginning of the semester. And we also talked about during the derivative discussion. It turns out that if we take the limit of this summation as the number of partitions go to infinity. So what does it mean? Let's think about that. Let's say we have a surface, like we have a region between A and B. So this is the graph of y equals f of x. And we would like to find the area under this curve between the points A and B. So let's say we use infinitely many partitions. In that case, what would be the width of each rectangle? So we are using very, very thin rectangles because there are infinitely many rectangles here, infinitely many partitions. So in fact, the width of each rectangle will be approximately 0, right? The limit would be 0. And we denote it by dx. So dx means that we used infinitely many partitions, so we just divided the interval to very, very thin intervals, so that it's like a line, not a rectangle anymore, right? So it is a very thin rectangle, and the width denoted by dx is approximately 0, okay? Because if you have infinitely many subintervals. So in that case, whether you use the left endpoint or the right endpoint to determine the height of the rectangle, then you take the limit as number of partitions go to infinity. So here there are n partitions, right? We just used n. So when we have infinitely many partitions, so this is equivalent to saying that dx goes to 0, the width of each rectangle goes to 0. In that case, the sum of these small rectangles will be equal to the area, like the blue area in this case, that we are looking for. So I equals 1 to n. So what we do, we just take the limit as n goes to infinity, and it doesn't matter whether you pick your height from the left endpoint or the right endpoint. Okay, so it turns out that when we increase the number of partitions, we will get exactly the value, the same value with the area of the blue region. Okay, this is what we will be calling as the integral. Okay, so the integral from the point A until the point B of this function f of x dx. So remember, we always had dx when we talked about the antiderivative. So in fact, what this means, this is the area under the curve y equals f of x between the values x equals a and x equals b. Okay, so this area is given by this integral. And so realize that we discussed about creating, like finding the areas of specific sub-rectangles. So f of x stands for the height of each rectangle, and dx, which is the very tiny, thin interval, is the width of each interval. So when you multiply width and height, so this is in fact the limit of the sum of each height, so let's just say it, times delta x when I is changing from 1 to n. So this is what we discussed when we found the area of approximating areas from subrectangles. And we mentioned that as we increase number of partitions, so this limit, we just call this the integral, okay, as n goes to infinity. So the definition, I mean, when you see this symbol, okay, the integral symbol from a to b, f of x dx, that means this is the area. So this integral now gives us the area under a curve, the curve y equals f of x, between 2 points a and b. Okay, I would like to show you this example. So for example, this is the graph of y equals x squared. We would like to find the area under this curve from 0 to 2. Okay, so from 0 to 2, we would like to find the area that is under this curve until the x-axis. So we just used, I mean, here in this example, only 4 subintervals are being used. So one subinterval is until 0.5, until 1. So each subinterval has the width 0.5, okay? Because we divided the interval 0 to 2 into 4 subintervals. And if we happen, so here it says use the left endpoint and right endpoint approximations. So in this case, the first one, if you use the left endpoint approximation, in the first interval, the height will be 0. In the second interval, so this will be the height. In the third interval, the left endpoint, this will determine the height. In the fourth subinterval, this point will determine the height of this rectangle. So just multiply the width of each subinterval, which is 0.5, by the height of each subinterval. So how do you find the height? Well, the first one is 0, so there is, because the function is 0 here. In the second one, just plug in to the function 0.5. Okay, so this endpoint. And this is the square function, so we would just need to take the square of it. So in the second, well, in fact, it's shown in here. Sorry. So this is the area of the first rectangle, which is 0. The area of the second rectangle is 0.5, which is the width, times 0.5 squared, which is 0.25. Okay, so the height and the width. So you can just find an approximation. So in this case, the left points give 1.75. The width is always the same because we just divided this interval 0 to 2 into 4 subintervals. So each subinterval has the same width, delta x equals 0.5. But the graph goes like this, right? So width is constant, 0.5. So this is 0.5, 1, 1.5. So those are where you divide your intervals. But the difference between those 2 points, it's always constant, 0.5, right? 1 minus 0.5, 1.5 minus 1. So the width is constant. How about the height? Well, look at this sub-rectangle. So as we said, we can pick the left endpoint or we can pick the right endpoint. And so here, if you just pick the right endpoint, you will have a larger rectangle. If you pick the left endpoint, you will have a smaller rectangle. So you have different approximations. And how do we determine this height? So because this is the function y equals x squared, well, we can evaluate the value here. Because here, the x value is 2. So f of 2 will be 2 squared, which is 4. You see here, this is what we just evaluated here. Using the right end points, right? It's denoted by r, right end points. The width is 0.5, the height is 4. 4 is found by plugging in the points to the function. Okay, so here you see that using the left end points gave us a smaller, well, in fact, the approximation is here, 1.75, an approximate area. Using the right end points gave us a larger area. So one of them underestimates, one of them overestimates. But eventually, when you, if you just, so here we just use 4 rectangles. But if you keep increasing the number of rectangles you use, then both approximations will reach to the same limiting value. So the more approximations, I mean, the more rectangles you have, the better the approximation. Let's see an example where we just approximate some area using some rectangles. Find a lower sum for this function on the interval 1 to 2 with 4 subintervals. So in fact, we would like to estimate the area under the graph of y equals 10 minus x squared between x equals 1 and x equals 2. Okay, so this is what we would like to do. Well, 10 minus x squared is a parabola. Let's just check the graph. So it looks something like this. Okay, so let's say this is the graph of y equals 10 minus x squared. So let's say this is 1, well, and this is 2. So we would like to make 4 subintervals. So the interval we are looking at changes from 1 to 2. So the total width we will be discussing will be 2 minus 1, which is 1. Okay, so this is the total distance on our subinterval. So we would like to divide it into 4 subintervals. So delta x, which is the width of each subinterval, will be what? 1 over 4, because there are 4 subintervals, which is 0.25. So what are these endpoints of the subintervals? So this is 1, this is 1. Let me just make it larger. So we are just looking at between 1 to 2, and we divided it into 4 subintervals. So the distance between each point should be 0.25. So this will be 1.25, 1.5, and this will be 1.75. So we would like to find a lower sum. So let's see whether we should use the right endpoints or left endpoints. Well, let's see. So this is the look at the first region. So this is our first region. Does the left endpoint or the right hand point, which one has a smaller length? So here, because this function is decreasing, this point is lower, right? So in fact, we should use right endpoints. Okay, so in the first interval, so for this rectangle, we will just make use of this point. Now let's write what is the area in the first subinterval. So this is the first subinterval. Okay, so this is the first subinterval. Let me call it A1, the area in the subinterval. So width times length. Width is constant, which is 0.25. How about the length? So we will find it by plugging in the right end point. So this is the right end point into this function, okay, into the y function. Okay, so this will give us the height of this rectangle, the y value at this right end point, and multiply it with the width. So that's going to give us the area of the first rectangle. So let me first write all the areas. So the second area is width times length. So it is constant 0.25 in the second interval. So now we are just looking in here. So the second interval, it is here. And what will be the height of this, or let's say the length of this rectangle? It's going to be given by the right end point, so which is going to be f of this point, like the right end point, which is 1.5. So the third rectangle, again, the width times length. The width is constant, and this is the third interval, like third subrectangle. So this is the third interval. So the height will be determined by the right hand point here. So this point, which is 1.75. So we will evaluate the function at these points, and let's write the last area. So width times length, which is 0.25, so the last one in here, times height of this interval, which is f of 2. Okay, so the last point. Area will approximately be the sum of these. Let me just copy these expressions. So in fact, realize that we have 0.25 common, f of 1.25 plus 0.25 times f of 1.5 plus 0.25 times f of 1.75 0.25 times f of 2. So we can in fact factor out the 0.25. So what we need to do is just plug in and evaluate the function at these points, f of 1.75 plus f of 2. And what is our function? The function was 10 minus x squared, right? Let me double check. So it is 10 minus x squared. So I will continue here. 0.25 times 10 minus 1.25 squared. Okay, so this is f of 1.5 plus 10 minus 1.5 squared plus 10 minus 1.75 squared plus 10 minus 2 squared. Let me just show. So this is f of 1.25. This is f of 1.5, f of 1.75, f of 2. Okay. So this will be 0.25 times. Well, if you add 10, 10, 10, 10, you will find 40 minus this squares of these numbers. So, well, I think it's time to use the calculator. I think we simplified it enough. 0.25. If you have a scientific calculator, that would work too. Times 40 minus 1.25 squared minus 1.5 squared minus 1.75 squared minus 2 squared. Okay, so for completeness, I didn't replace the value of 2 squared with 4, so just subtract these values. So let me just hit enter. It found 7.281. Okay, let's double check. Yes, so we got the same thing, 7.28, right? So 281 we said. So this is the lower sums. So this is an approximation of this area. It underestimated this area, and so it says it's an underestimation because there are parts which we didn't take into account, okay? Because these rectangles didn't evaluate these parts.